you, Ray, for the kind words. And thank you, John and Jim, if you're online, for organizing this seminar series and inviting me to participate. As the title indicates, I would like to tell you about potential field applications to understanding Cascadia crustal structure and so forth, and what that might have to say about earthquakes. So first things first, there's a cartoon. I'd like to credit just a few of the people that have helped me along the way to understand the Pacific Northwest. Ray, of course, is at the top of the list, and I imagine some of these people are maybe listening in online as well. Well, I don't need to tell this audience about Portland's position in the middle of wholesale tectonism and magmatism related to the Cascadia subduction zone. So I won't belabor this slide very long, except to remind you that the subduction of the Juan de Fuca plate beneath North America is responsible for three classes of earthquakes. There are the megathrust earthquakes, the great earthquakes that occur on the locked zone between the upper and lower plates. This happened about every 500 years here, and the last time it happened here, magnitude 9 earthquake was 323 years ago. Second class of earthquakes occur within the slab as it passes through critical depths and goes through some important metamorphic changes. These earthquakes happen frequently, reach, say, magnitude 7. But this talk is about the earthquakes that occur in the upper plate on crustal faults that are responding to the stress and strain of the moving plates. Now, these faults don't produce earthquakes very often, but on the other hand, we know the faults lie beneath all of the metropolitan areas of the Pacific Northwest, and understanding their properties is just prudent in trying to mitigate their hazards. So the Pacific Northwest is a region of profound tectonism and magmatism. The blue lines on this map are quaternary faults from the USGS Quaternary Fault and Fold database. The yellow dots are upper plate earthquakes, and the red triangles are quaternary volcanoes. I'm going to focus on three parts of Western Oregon, or Northwestern Oregon, and Western Washington. The Puget Lowland and the Portland Basin and Willamette Valley are in the forearc. By that I mean that piece of territory that is west of the Cascade Range, the arc, and the actual subduction margin. And then in the back arc, on the east side of the Cascade Range, are the Yakima Fold and Thrust Belt. Well, we've seen this slide, I think, at least twice so far in this seminar series. It's a magnificent slide map that shows the velocity of the Western United States relative to North America. Two big things are going on here. The whole area is rotating clockwise at the rate of about 1 or 1.5 degrees per million years around a pole that's located in central Idaho. And then superimposed on that are the great big vectors along the coast pointing to the northeast. These are of the elastic strain as the Juan de Fuca plate is jamming into North America. It's squeezing the coastline towards the northeast, and that's elastic. So the next time we have a magnitude 9 earthquake, presumably these vectors will shrink to almost nothing. So it's recoverable. We can subtract that elastic strain from the total vectors and come up with the permanent strain, the stuff that has to be accommodated on faults and folds. It's about 6 millimeters per year northward in the forearc, about half that in the back arc. So I think there may be some undergraduates in the audience. So I thought it'd be appropriate just to say a few words about what I mean by potential field methods. This is Sir Isaac Newton. He's just discovered the attraction of gravity. So this is Sisyphus, who's learning about potential theory. He's trying to move an object through a force field, and as we all know, that takes work. As he moves the rock up the hill, he's increasing the rock's potential energy. And in principle, we could know the potential energy any place in free space, and that's the potential field. certain class of potential, a certain class of force fields, the energy change and going from point A to point B is independent of the path taken. That's called a conservative field. And it just means that we can represent the relationship between the force field F and the potential phi with that really simple differential equation. Well, so big deal, who cares? Well, the mere fact that that equation exists for gravity and magnetic fields means that we have access to this elegant body of mathematical theory known as potential theory. And from that, we can develop all sorts of tools to analyze gravity and magnetic data. So rocks are magnetic. Every rock is magnetic at some level, as it turns out. And there's two kinds of magnetization in a rock. There's the induced magnetization, M sub I, which points in the direction. Well, as the name implies, it's induced by the Earth's magnetic field. It points in the direction of the Earth's magnetic field, and it's proportional to the Earth's magnetic field. And that proportionality constant is chi, or magnetic susceptibility. The other magnetization is remnant magnetization. It's a semi-permanent property of the rock. It's caused by it's related to the geologic history and evolution of that rock. For example, thermal remnant magnetization is acquired by a magma when it cools to below the temperature of the magnetic minerals in the rock, usually magnetite. So if you rotate a rock, the induced magnetization always points in the direction of the Earth's field. The remnant magnetization rotates with the rock. This graph compares magnetic susceptibilities for the rock types. And there's two things to note here. First, the average susceptibility for a basic igneous rock like a basalt is something like 25 times more than for a sedimentary rock and for metamorphic rocks as well. So basalts are very magnetic. That's the point here. The second point is that the error bars indicate how variable this physical parameter is, enormous variability from point to point, which makes interpreting magnetic fields particularly interesting. This graph compares remnant magnetization with induced magnetization. Q on here is the ratio of the remnants to the induced magnetization. So if you study this graph for a little bit, you'll see that these are basalts, Columbia River basalts, and the remnant magnetization is 10 to 100 times greater than the induced magnetization. And that makes interpreting magnetic anomalies even more interesting because we rarely know the direction of the remnant magnetization. We make magnetic measurements in various ways, and everything I talk about today will be data collected with a fixed wing aircraft. Here you can see the magnetometers attached to a boom extending out from the aircraft, trying to get the sensors away from the magnetic field of the airplane and the motor. And there's actually some sensors on the wingtips as well. So as Ray mentioned, the USGS has been systematically acquiring aeromagnetic data from the Pacific Northwest for the purpose of, since 1995, for the purpose of mapping and characterizing crustal faults. And the point is made here with this cartoon. About 90% of the Earth's magnetic field that we're experiencing in this room right now is coming from the Earth's core, from complicated, complex magnetohydrodynamic movements in the fluid core. The other 10% comes from magnetic minerals in the upper crust. That part of the crust that is cooler than the Curie temperature of the magnetic minerals. Mostly that's usually magnetite, and the Curie temperature is 580 degrees centigrade. So the magnetometers sailing or flying through this field is experiencing the total magnetic anomaly, total magnetic field. But with our data processing techniques, we can isolate the crustal signal specifically, and that's depicted by this yellow wiggly line. As we go over a magnetic body, magnetic source, the crustal magnetic field rises and produces what we call a magnetic anomaly. If we fly the airplane, or in this case a helicopter, back and forth across the ground, here I put a fault through a magnetic layer. It's called a volcanic lava flow. It's completely concealed by less magnetic material. That little bump in the magnetic layer produces a small little perturbation on the crustal magnetic field. And if we fly the airplane back and forth, as done here, we develop a map of that magnetic field along the fault zone. And then from the map, we can get out our red pencils and start drawing lines on a piece of paper and try to interpret what that means in map form, as well as trying to learn about what the sources look like beneath the surface. Okay, gravity is another important potential field, and it's very useful because rocks have different densities. The yellow arrow points to basalt, and you can see that the density of a basalt is greater than all sedimentary rocks on this graph and most of the metamorphic rocks. So that's the important point here is that basalt is both magnetic and dense usually. So what we measure at the Earth's surface is the gravitational attraction of the whole Earth. The contribution from geology is it's a very small part of that total gravity attraction, as this fellow is noticing. And so as he moves across this fault from a dense rock to a lighter, less dense rock, he's changing his weight just a little bit. We can isolate that crustal signal, as in the magnetic case, with our data processing. We make gravity measurements, again, in various ways. By far, most of the measurements on shore are done with point measurements using a gravity meter. That's yours truly showing you his best side. And that's happens to be Stewart Valley near Death Valley, California. And this is Portland State University's very own Scott Brownston, who did a master's thesis here at Portland State. I had the privilege of working with Scott. That was quite a long time ago now. He was studying a couple of lakes, a couple of basins at the California-Oregon border near Klamath Falls. Okay, let's take a look at the magnetic surveys. As we fly these surveys as close to the ground as the Federal Aviation Administration will let us fly, and is able to be done safely. So, that, as you can see from this cartoon, these guys got a little too close to the ground, picked up a passenger. This map shows the aeromagnetic data that we have acquired over the last, well, since 1995. The brightly colored regions are high quality data that's flown at about 400 meters along lines that are spaced 400 meters apart, as close to the ground as we can get. We try to aim at 200 meters above the ground. Sometimes we can't make that because mountains are in the way and pilots are concerned about that. Okay. So let's put that data set on this map. This is, of course, Northwestern Oregon, Western Washington. Again, it shows the quaternary volcanoes, earthquakes, and quaternary faults. The blue pattern is the location of the high resolution USGS aeromagnetic data. Done a pretty good job of covering this area so far. This was funded by various USGS programs, including National Geologic Mapping, earthquake hazards, volcano hazards, also some money from FEMA and from the Umatilla tribe. Now, there's one glaring hole you'll see right here in the Cascade Range. I'll have more to say about that momentarily. So these data allowed us a few years ago to postulate connections, for example, between the Yakima fold belt over here, which is active, and faults in the Puget lowland, which are also active. We wanted to know if these were kinematically connected. And that allowed us to, these data allowed us to make that hypothesis. The dashed lines on this map show our best guess at how these two regions are connected by faults from the back arc to the fore arc. We've wanted to do this for a long time. At the southern part of the Yakima fault belt, which they're all lined up pointing right at Portland, do these faults extend beneath the Cascade Range and perhaps interact with the northwest striking faults west of Portland? Well, as luck would have it, we managed to acquire funding recently to fill in that gap. Two surveys, one was flown in 2021, it's the southern half. We call it the Cascade Locks survey. It included Adams and Mount Hood. And then just 2 months ago, we finished a second survey, the second half of this pink area, which went around Mount Rainier and included the Mount Rainier and the West Rainier, and the Mount St. Helens and West Rainier seismic zones. Here on the left, I put together all of the data at our disposal, the new data, plus filled in around the edges with, frankly, crappy data, but there you are. And to me, this is, in my humble opinion, it's a remarkable map. To me, it's a proxy for a subsurface geologic map. It shows, for example, the Devil's Mountain Fault, the Doty Fault is right here. It shows clearly the folds of the Yakima fold belt, the Gales Creek Fault, and the Corvallis Fault. On the right is the gravity map of the same area. And this gravity map has been processed in order to emphasize middle to upper crustal sources. The anomaly that probably catches your eye first is this whomping big anomaly along the Coast Range. It's caused by Eocene basalt, the Siletzia terrain, which I will describe in just a moment. And to the east of that are a lot of more subtle negative anomalies, and they're over sedimentary basins. The basins are filled with low density sediments and floored by more dense rock, often volcanic rock, and produce therefore negative gravity anomalies. So the foremost expert on Siletzia is sitting in the second row, Ray Wells, but I need to talk about it before I go forward. So I'm going to do my best Ray Wells imitation here. The Siletzia, or Siletzia terrain, as I'm going to call it, is shown on this very simplified geology map by the black blobs. So that's the exposures of Siletzia terrain. It's Paleocene to Eocene basalt of oceanic origin, a plateau basalt that was erupted in the early Eocene and immediately jammed into Oregon and Washington. It forms the basement of the Oregon and Washington Coast Range. It's composed of 3 different formations. In Vancouver Island, it's called the Machosen Formation. In Washington, the Crescent Formation. And in Oregon, the Siletzia River Volcanics. As I mentioned earlier, the basalts are very magnetic and they're very dense, and that is certainly true of the Siletzia terrain. As Wells and others noted quite a few years ago now, the extent of Siletzia terrain in Washington and Oregon is represented in the magnetic anomalies by this black dotted line. So the black dotted line indicates the eastward margin of Siletzia. I remember that I showed you the Siletzia exposures are along the coast, but the geophysics tells us that that terrain extends concealed all the way beneath the Willamette Valley into the Western Cascades, beneath Portland and Vancouver. The Siletzia terrain is about 10 kilometers thick in Vancouver, 20 kilometers in Washington, and up to 32 kilometers in Oregon. And this seismic refraction section from Trehue and others shows the Siletzia terrain extending down to somewhere between 23 and 33 kilometers in thickness. So in the remainder of the time, I want to discuss 2 things that I think we can contribute with the magnetic data. The first is, do the Yakima folds and faults extend westward beyond their mapped extent? And the second is, can we learn something about the deeper fabric of Cascadia from these potential field data? So the first one, do the Yakima folds connect to Portland? I'm going to now zoom in on this yellow rectangle. It's the so-called study area for the rest of this talk. Now, these are the same magnetic anomalies, and they've been reduced to the pole. And if there are undergrads in the audience, I should explain what I mean by that. The shape of a magnetic anomaly depends, of course, on the shape of the causative source and its depth. It also depends on the direction of the magnetization and the direction of the regional ambient field. Only if these two vectors are vertical is the magnetic field centered over the causative source. So we can eliminate that skewness produced by the dipping vectors with this process called reduction to the pole. It's essentially a mathematical filtering operation that rotates the vectors to a vertical direction and then slides that anomaly directly over the causative source. But I like to go one step farther, and I think most of my colleagues in the USGS feel the same way, and that's to let the computer actually help me draw lines around the magnetic sources. And to do that, we exploit the fact that gravity anomalies, not the magnetic anomalies, but gravity anomalies over tabular bodies have their steepest horizontal gradients at the edges of the tabular features. So it's a three-step process. We first transform the magnetic anomaly into what's called, a funny name, pseudogravity. It's still a magnetic anomaly, but it's been mathematically transformed into the mathematical equivalent of magnetic data. So it's a mathematical trick to get the anomaly caused by this body to have its steepest gradients over the edges of the body. The second step is easy. We calculate the maximum horizontal gradient that puts peaks over the edges of the body. And the third step is to search for those peaks and plot them on a map. And they tend to line up in lines, as shown on the map on the right. This is the Northern Nevada Rift. So it's quick and dirty. This takes maybe 10 minutes on the computer to come up with a first cut interpretation of what's causing the magnetic anomalies in map form. Well, this very busy map we call these MAC spots, by the way, affectionately. This is a map showing all the MAC spots for the magnetic data that we've been talking about. It's a busy map, but if you look carefully, you can see some very clear lineaments. It's just an objective map because very few assumptions are underlaying the calculation of these dots. The next map is not objective, it's subjective. It's my interpretation about which of these lineaments are significant. The black lines on this map are my call on the most important boundaries between magnetic rock and less magnetic rock. It could be many different things. It could be a magnetic pluton that's intruded into less magnetic country rock. It could be the edges of a lava flow, or it could be a fault that has brought magnetic rocks next to less magnetic rocks. Well, we know that some of these lines are faults. The arrows are pointing to the Olympia Fault, the Doty Fault, the Horse Heaven Hills anticline and its faults, Gales Creek and Corvallis faults. We know these are faults because they've been mapped in other ways. And it stands to reason that some of the other black lines on this map could be faults. We don't really know that unless we have independent geophysical or geological information, LIDAR information, paleoseismology, you name it. But given that caveat that I fully understand, I'm going to go ahead and propose that we have aeromagnetic evidence to connect the Yakima fold belt to Portland. If you look at the area that I've outlined in the east here with a red dotted dashed line, all of the lines, contacts, magnetic contacts, are oriented northeast, southwest. And they move on into the Portland area where they run into a set of lineaments that are oriented northwest, southeast. And as I'll show you, well, in the next slide, I interpret this to mean that we have specific faults coming from the Yakima Folds, the Horseheaven Hills, and the Columbia Hills anticlines into the Portland area where they meet northwest striking faults, that some of which are mapped. And this might be a kinematic connection between these two regimes. So compressive forces on these thrust faults and strike slip displacement on these northwest striking faults. So let's take a look at both ends of this package. At the east end are the Yakima Folds. This is a Google image, no vertical exaggeration, looking to the west towards Mount Rainier. It's clearly a region of wholesale compressional deformation. And for the students in the audience who haven't made the trip, put it on your bucket list. Take the drive from Ellensburg, Washington, down the Yakima Canyon to the city of Yakima, and you go through this terrain, and you can't escape the conclusion that you're in the middle of an amazing compressional geology. Now, Lydia Stayish in our group made the same point with geophysics. She and her co-authors produced this model of the Umtanum Ridge anticline. It's one of the Yakima Folds. So this is a method that's very common in potential field interpretation. It's a forward model. So what Lydia did is to use geologic mapping and geologic intuition to divide the crust up into a series of geologic bodies shown by these different colored polygons. She assigned magnetization and density to each one of these. And then she used a computer program that allowed her to move the corners of the polygons around using geologic intuition the whole way in order to produce a fit between the calculated magnetic and gravity fields and the observed. And this is her favored model for the Umtanum Ridge. And the bottom line is she predicts from this that there's about, what does it say, 2.4 kilometers of horizontal shortening north-south across the Umtanum Ridge anticline. I will quickly point out that there's evidence from geophysics that strike-slip faulting is also significant, less significant, but it's there in the Yakima Folds. This is an amazing magnetic map. It shows this low anomaly that's striking west-northwest, east-southeast across the map. It's the Wallula Fault, one of the Yakima faults. And oblique to that are a series of parallel anomalies that are striking northwest, southeast. These are caused by 8.5 million year old dikes, the ice harbor dikes, the waning stages of Columbia River basalt eruption. And we argue that these northwest striking dike anomalies are not continuous across the Wallula Fault. They've been offset by right lateral motion on the fault. Let's move to the west side now. Now, Ashley Stregg showed this figure last week. It's the Gales Creek Fault. The Gales Creek Fault is a northwest striking 60-kilometer strike-slip fault southwest of Portland. It's been studied extensively by Ray and colleagues. His interpretation is based on new geologic mapping and new aeromagnetic data. Here's a magnetic anomaly over the Gales Creek Fault, and it shows that his interpretation is that this chunk of rock has been displaced 12 kilometers to the northwest along the Gales Creek Fault. It's Eocene basalt, so Eocene in age, moves 12 kilometers since that time. I should point out that the cross-section on the right is produced from the magnetic and gravity data in the same way, and it points out that it's not a simple strike-slip fault. It's a transpressional fault. It's undergoing both strike-slip deformation as well as compression, producing these little pop-ups like squeezing a pumpkin seed between your fingers and pushing it up. There's evidence that the 60-kilometer long Gales Creek fault extends and connects with the Mount Angel fault to the south, which gets us all the way down to somewhere here, Salem, essentially doubling the length of the fault zone. The Mount Angel fault produced a magnitude 5.7 earthquake in 1993, called the Scotts Mills earthquake. The epicenter was only 60 kilometers from here. It caused $30 million worth of damage in dollars at that time. Now that amounts to $52 million. I'm almost embarrassed to even point that out because $52 million is nothing compared to what's going on in Turkey and Syria. However, it can be in Malala or small little towns, and $52 million is a lot of money. And you can imagine what those two towns would look like if it had been a magnitude 7.5 earthquake, which I think is quite possible on the combination of the Mount Angel and Gales Creek faults. I'm going to skip this slide. Let's zoom in quickly on the Canby-Malala fault. Here is a little tiny two anomalies on either side of the fault, right where the Willamette River takes a right bend. And these two anomalies are displaced by about 3.5 kilometers. These anomalies are caused, I'm pretty sure, by Columbia River basalt, so Miocene in age, 3.5 kilometers. The profile on the right is a quick and dirty magnetic model showing that it also requires some vertical displacement. So the conclusion here is that I think we have aeromagnetic evidence that faults of the of the Yakima folds are moving their way into the Portland area, and they're getting very close to the faults to the west of Portland to strike northwest southeast. And now I'll admit this is just speculation. We need to get on the ground, do some geologic mapping, get some good LiDAR data, Ian, I probably have some, and see if there is a kinematic connection between these two fault regimes. Okay, let's move to the last topic. I want to use these magnetic data. Well, you probably got the feeling from what I've said so far that I'm pretty excited about the short wavelength information in these data. It allows us to learn about the uppermost crust and the faults in the uppermost crust. Well, now I'm going to throw that away and look at the long wavelength information to try to look a little deeper into the crust. I'm going to use a well-known tenet of potential theory, and that is that the spectrum of a magnetic anomaly has a shape that depends on the depth to the source. Specifically, you take a patch of magnetic data and you calculate the Fourier transform and the power spectrum, the log of the power spectrum. As the wave number increases, the slope of the spectrum is proportional to the depth to the source. So this is a 5-step procedure. It was developed by a colleague in Denver, Jeff Phillips. First, we calculate the power spectrum. Second, we fit straight line segments to that power spectrum. That gives us the depth to the various layers beneath us. Given those depths, we can calculate, we can derive matched filters that emphasize anomalies coming from those depths. And then we can run our magnetic data through those filters to enhance the anomalies, to emphasize anomalies coming from those depths. And finally, we can map the context using MAC spots that I discussed briefly just a few minutes ago. So let's take a look at one example. This is a small little patch of ground in the Western Cascades near St. Helens. It's 50 kilometers on a side. These anomalies at the surface have lots of different rocks, everything from quaternary deposits to the Chelas Cascades transition and Eocene age. And this is the power spectrum that those anomalies produce. The observed power spectrum is the pink line, and the green is the best fit to that. And that fit was made by me deciding where the straight lines should be on that gentle decaying spectrum. So I made the assumption that there were 3 geologic layers to consider. That's a big part of this. But there are actually 4 layers. There's a layer called layer 0. That's noise. It's very, very tiny, but we can't get away from that. The data aren't perfect. There's round off. There's a little bit of noise from the aircraft itself. And there are some errors that are caused by navigational and data processing problems. The first geologic layer is about 1.5 kilometers thick. I assume that's volcanic terrain. We're in the Western Cascades here. Beneath that is a weakly magnetic but very thick layer that I'm going to guess is sedimentary rock. As I'll show you in a moment, Dal Stanley thinks that this particular piece of ground is underlain by Eocene marine sediments. And then the basement is probably Northcraft Formation, the very early stages of the Cascade Arc volcanics. So now that I have those layer depths, I can run the data through those filters and see what the anomalies look like at those depths. So this is the shallow layer at the top, and the deep layer is layer 3. Well, just as luck would have it, this is actually pretty interesting, I think. If you look at layer 1, I think I see an evidence for a northwest-southeast striking fault. Would you agree? That looks pretty good to me. I can't tell very much about that fault, but if I look at that same line on the deep layer, it looks like the rocks that are causing this deep anomaly are offset in a right lateral sense, about 10 kilometers. And those rocks are, if they're Northcraft Formation, they're Eocene in age. And so 10 kilometers since the Eocene. But why stop at one sub-area? I've done this for 17 areas all the way across the arc, and across Cascadia. Here's what that section looks like. Let's just talk about the basement. It ranges from about 9 kilometers deep to 4 kilometers. What is it composed of? I think it's composed of many things. It's almost certainly got to be Siletzia terrain on the west, and it's probably pre-tertiary inlier rocks on the right, and Northcraft Formation in the middle, and who knows what else. All right, moving on. I've done the same match filtering approach to the entire area, and that's shown here. So these are the magnetic anomalies enhanced for what the spectrum tells me is the most important deep layer. It's about 10 kilometers deep. So these magnetic features are coming from deep within the magnetic layer. Let's first just zoom in on the St. Helens and West Rainier seismic zones. The West Rainier and the St. Helens and the Goat Rock seismic zones are these north-northwest striking earthquake zones that are fascinating. And I don't think it's a coincidence that this northwest-southeast strike of the seismic zones are the same as the strike of the magnetic anomalies. In fact, the 2 seismic zones lie within low magnetic regions. And I wonder if the magnetic anomalies are weak there because these are zones of crustal weakness, fracturing, perhaps. And just I throw that out as a possibility. Now, superimposed on here, this red blob is the Spirit Lake Pluton, Oligocene, I believe. Now, it doesn't seem too much of a leap to say, well, that's where it sticks out of the ground, but this oval-shaped anomaly is the Spirit Lake Pluton at depth. And so again, the 2 seismic zones, they seem to be avoiding this Pluton, as if the Pluton is acting as a stress guide or whatever, helping to keep those earthquakes lined up where they are. Now, there's an enigmatic electrical conductivity anomaly that's been discussed about for decades in here. It's called the Southern Washington Cascades conductor. It was discovered in 1980 by Law and others, and it was interpreted in 1990 by Hill as a magma chamber. Dal Stanley and co-authors interpreted it as not as anything related to heat at all, but as a wad of a wad of Eocene marine sediments. Well, those interpretations have always bothered me because it shows this drawing from Stanley and others shows the conductivity zone completely ignoring this big pluton. It doesn't seem reasonable to me. Well, there's a recent paper that I recommend by Paul Bedrosian and others. It's published in Nature Geoscience. They used magnetotelluric data, three-dimensional inversion, and came up with this rather interesting model for what's causing the Southern Washington conductor. They see a mush zone, a 3 to 10% partial melt at about 12 kilometers deep, and sedimentary beds that go up around the Pluton. The Pluton is, they call it the batholith, Spirit Lake batholith, and that's a channel for fluids and magma to move towards the surface. So it's the same conductivity zone, but it's much more complicated and therefore, in my mind, much more realistic. All right, one last thing to point out. Here I'm showing the Siletzia terrain by the black blobs, and the black dotted line is from Wells and others as the extent of Siletzia terrain in the subsurface. With this magnetic map, I think we can do a little better job of drawing that black line, just slightly different. There's this pinch pooch right here at about just north of the Columbia River, and a low in the deep magnetic anomaly that strikes southeastward across the entire forearc and into the Cascade Range. And I wonder what the heck that is. It's, there it is outlined. It is right along a series of synclines that also go all the way across the arc. It's related to the Doty Fault shown by the red line here. And I wonder if it's a trough, a structural trough that is dissecting the coast range and the forearc from north to south. It also includes the Chehalis Basin, a green oval. Here, that swath is put on top of the gravity data, and it's certainly disrupted at the same place. In Oregon, the Coast Range gravity anomaly is fairly continuous, probably because it's a really thick mass of rock, 30 kilometers thick. As we move northward, it becomes thinner, becomes, I suppose, more plate-like and broken up into blocks. And one of those breaks is right here at the, I'm calling it the Chehalis magnetic trough. And you could even use your imagination that the Coast Range gravity high is offset right laterally at that location. A few years ago, I did, before I knew about this feature, I constructed a model right across here based on this cross-section from Wells and Johnson. They modeled the Doty Fault as a steeply dipping reverse fault and a hanging wall syncline to the south, floored by crescent formation, Siletzia terrain, and filled with Eocene and younger sediments. And I used that as a guide to construct a gravity and magnetic model across there. And so here I've modeled the Doty Fault as a thrust fault, floored by crescent formation and filled with sediments. Well, now I think my plan is next to go back and look at this, step back and look at this in a much bigger way, because the magnetic analysis I just showed you shows that this feature may extend significantly deeper than shown by this simple model. One last thing. Most of the slip at a megathrust are the great earthquakes, but there's also slow slip that is going on continuously at the Cascadia subduction zone. It's accompanied with low frequency tremor. It's called ETS, episodic tremor and slip. And this is data from another paper by Ray. It shows the frequency of tremor up and down the coast range. So the color contours represent the number of tremors within a square kilometer as averaged over a 6-year period. Well, the tremor density is reflecting activity on the subducting plate, but it's not continuous north-south along the subduction zone. Very interesting. It's discontinuous. And this was pointed out by Bassett and Watts and then by Wells and others. And they kept carrying it a bit farther, at least Wells did. They noticed that these breaks in tremor density occur where there are major trans-forearc faults cutting across the forearc. I should have put them on here, but the Corvallis fault is about here. The Gales Creek fault is about here. And then the Doty fault is up there. And I just point out that the Chehalis magnetic trough is in one of the, well, their interpretation of why this happens is that the faults are so profound, they extend to great depths to near the megathrust itself, where they tap the high pressure fluids and provide pathways for those fluids to get away from this subduction contact and influence the speed, the frequency of tremor. Well, I think I've said enough. I'll just leave you with a couple of points. First of all, there's high resolution. Yeah. I need to keep this cartoon always in mind because there's high resolution aeromagnetic data now cover much of Cascadia. These data are published, freely available. You can download them off the web right now. If there are students out there who think these data might be useful in your work, please just let me know. The aeromagnetic surveys, I believe, have helped us identify, map, and characterize active Cascadia faults. More work is needed, as always, as the saying goes. And I am in the process of trying to use these data to look a bit deeper into the crust with matched filtering. And this is definitely a work in progress. Thank you.